Other issues with humidification, and I think you will talk about that a little bit, condensation on windows.
A little bit.
Okay, well, leave that alone. We already talked a little about condensation. Are you going to talk about air tightness, building envelope, and too tight? Do you want to?
That's them, not me.
All right. I'll skip.
I'll probably be doing the same thing you're doing at the end of month.
I'll skip over to my case study. This is a project in New Haven, Connecticut that I worked on as a young engineer in the mid-90s when I was actually still, running all these analysis tools and struggling with this. This is a Sterling Memorial Library, which is sort of the centerpiece of their campus, and where they keep, I think, about $1 billion worth of books and collection and research pieces and artifacts. And that building was in pretty tough shape and needed a substantial exterior envelope upgrade and upgrade of the interior environment. It's just a photo of the thing under construction in 1929, and you can see that it actually has a patented book stack system. That's what all this matchstick stuff is that was erected first. And then the masonry skin just sort of was raised as a shell around it. So again, mass masonry wall, skin around this, matchstick book stack construction. I love this. I love this photograph. That's how they built it. Fast forward to the 1990s. The thing was in fairly rough condition, similar to the church in Albany that I showed you, that taken a little bit better care of it. It had been repointed once, various roof repairs, but the roofs were generally in poor condition. And then in the 1970s, they added plexiglass to all the leaded glass windows and operable sash in an attempt to keep energy costs down. The interior conditions were what was really bad. This is a view of the book stacks, which were actually right up to the perimeter of the exterior wall. They had water leaks below the roofs and had walls and windows. It didn't have any mechanical ventilation. People just opened windows, and then it rained in there and it got the books wet. And they had steam heat. And I remember walking in there, and it was just this cacophony of hissing steam everywhere and stuff squirting, and it was a real mess. And it had been like that for a while. So obviously the building needed some substantial intervention, both on a building envelope basis and also to look at the interior conditions. So the owner's goals here were really twofold, at least. The building is sort of an icon. Not the nicest building that they have, but it's very important to them. So they're interested in preserving the appearance. But they also had important rehabilitation needs that had to do with the repair of the facades and the windows, and to improve the storage conditions for the collection as much as they could. So the methodology that we employed is what engineers do every day. We investigate, we evaluate, and we present the owner with some outrageous options. Then there's some compromising going on. Develop a design, it gets built, and then you go back later and see how it does, and you learn and see how the thing is performing. We did an envelope investigation where we found out that the walls are surprised. There was no flashing there. They're completely wet inside. There was probably 60-year-old water in the brick masonry. It was nearly entirely saturated. The windows leaked air and water. Primarily at the window perimeter, right here. And if you imagine, the window just sort of sits against that limestone jamb, and the jamb is just very skinny at that point. That's where all the leakage comes in. And the roofs leaked, and the leaded glass was in poor condition. That's just some views of the leaded glazing. And this is a cross-sectional view of the wall assembly. Exterior stone facing brick. Here's the window perimeter. No wall flashing. So this is just, again, going back to the earlier point that I made, this is just a sponge that soaks up water and then lets it go, and if it leaks once in a while, people initially didn't get that bent out of shape. But now there were. So we used some pretty early analysis tools We used a program called Moist to do a simple vapor flow analysis for the north and south facing walls. We looked at previous operating conditions and new conditions, and we looked at options for adding insulation and vapor barriers. And what we found out is, similar to what we had anticipated, is that the walls can sustain some interior humidification without condensing on the interior surfaces. And I showed the slide earlier that made that point. But we decided to avoid adding insulation to the interior of the wall because we wanted to limit the risk of frost damage to the wet masonry. The envelope design goals, again, tried and true stuff. Make the wall system drier, keep it warm, right? Not adding insulation to it. Reduce air leakage and limit condensation potential, and then restore the leaded glass. So as a design solution for the walls, we put wall flashings in, and Eric, I put these slides in just for you. Okay, so we put in partial wall flashings above windows and belt courses, copings to just try to limit the amount of water that made it into that wall. Right? Obviously, if you want to stop that wall from leaking entirely, you have to clad it over with something, right? But you can do a lot of good by just looking at some fairly intensive areas where you get a lot of leakage. There's just that flashing in place and the water coming out on the outside. For the interior environment, the owner decided that they want to limit the humidifications just to the book stack, because that gave them more options to restore the existing leaded glass that was of a very high quality in the areas outside of the book stack, and that would have been difficult with high humidity environments. So in areas where we had high quality leaded glass, we restored that in a leaded glass shop and added a storm sash to improve the thermal performance and also for UV protection. There was a laminated piece of glass, and the laminate keeps the UV out. And yes, the storm sash was vented. And we improved the perimeter waterproofing. At the book stacks, and this is usually where people stop throwing things when they come to in front of architects. Unfortunately, we replaced the windows, and we replaced them with thermally improved, thermally broken aluminum frames and insulating glass units. And the other barbaric thing that we had to do to make this thing reasonably thermally efficient and cut down on the perimeter leakage is we had to cut off the stone jamb to insert flashing and insulation around the window perimeter. And I'll show you a photo of that. And the other thing that we did is we provided an interior heat fin to draw some beneficial heat into the window frame. So this is what things used to look like. We cut away the limestone and then put in a drainage layer. What you don't see here, then the window went in, insulation, the waterproofing membrane. There's a nice flashing at the sill to get the water out. And the window sits in there, and it gets, here's the original, here's an area that we reconstructed and bricked, and then it gets this is in the book stack utilitarian spaces, it gets a metal jamb surround. This is actually a piece of brake metal. And it also works as a heat fin to draw beneficial heat into the windows. And then those windows got what you will call the caricature of leaded glass, applied lead cames, and colored mylar to approximate the color of the existing leaded glass. And it won't fool anybody that's in this room when you're walking by it, but it fools 95% of the people that are walking by on the street. Right here you have original leaded glass, nicely restored. Here you have insulating glass units that have sufficient performance to contain that interior environment. Another thing that helped us out here is by cutting away that limestone jamb, we could actually hide that bulky aluminum extrusion in the frame. And we just had a 1-inch sight line, which actually matched what was on the original windows. Here's just some photos of the leaded glass being restored. For the environment design solution, the important thing here is that the curators actually allowed us to ramp the relative humidity between the summer and the winter time. So in the winter time, when we have high risk of condensation, if you have a severe cold snap and you don't want to see that condensation on the windows, that actually allowed us to ramp that down slightly to a 42 degree Fahrenheit wintertime dew point. The other thing that was critical to do here, we're allowed to actually program the system to get, during very cold spells, to have negative air pressure. And this is something that you frequently don't get away with curators, because if you have negative air pressure and you're drawing outside air into the building, they're worried that you're drawing mucky air into the building. But it helps in the wintertime because you're drawing dry exterior air through the envelope. So if you're pushing moist interior air through it, as we learned earlier, you would run into condensation problems. Okay? All right, I'm done. Conclusions. Historic buildings manage heat, air, and moisture in a fundamentally different manner than contemporary lightweight construction. Right? You got big, thick masonry walls that, are sort of living systems that absorb moisture and then give it off. And if you do something with them, they'll change their mind and they'll do it entirely differently. Upgrades or renovations to historic buildings must be carefully evaluated to avoid causing more harm than good. But I think, once we bring some technology to bear with careful analysis and design, the energy performance of historic buildings can be greatly improved if you responsibly use modern materials and methods.